Welcome everyone. My name is Daniel Zadęcki and I'm representing today Krakow Technology Park. It is great pleasure for me to be here today with you. So today I'm responsible for, and tomorrow, so of course for this whole D, Tech and VR. And we are starting now with the first presentation. Mr. Karlo, yes, please.
Thank you. My name. Hi, my name is Karlo. I'm first time here in Krakow. The city is very nice and it's a pleasure to be here. I'm from Crow team and I'm going to talk to you today about two performance optimizations we did in our engine for Serious Sam VR. Those are multi-GPU and single-pass rendering using LiquidVR and VRWorks extensions. How we managed to use them in our engine in the same rendering system, and some of the problems we encountered along the way trying to implement all that. Also, I would just like to note that since each engine is different, some of the problems that we've had won't be an issue at all for someone else, and it's likely that there are other problems and pitfalls that we, due to the luck in our engine design, didn't even found, but it will be a huge problem for someone else. So let's start. So what virtual reality is even all about? It's basically displaying moving images and playing sounds on a tracked head-mounted display that make the player feel they are actually physically present in a virtual environment. This could be a game or some other experience. Presence is basically the ultimate goal of VR. So how do we achieve that? In one of his talks, Michael Abrash gave a list of technical requirements for achieving presence. Those were wide field of view, resolution, refresh rate, low pixel persistence, global display, optics, optical calibration, rock-solid tracking, and low latency. So, other than the pixel persistence, global display, optics, calibration, tracking, which is handled by the hardware or the HMD driver software, the field of view, resolution, and refresh rate do need some help from the game programmer. So let's start with the field of view. VR needs a very wide field of view. Not necessarily as wide as human eye, but still wider than what is needed for regular desktop games. Both Vive and Rift have about 110 degrees FOV angles. As you can see in the picture, the main drawback of having a wide field of view is having to render more objects in any given frame. Onto the resolution. So resolution of the headsets is very high. It's 1080 by 1200 pixels for each eye, both on Vive and the Rift. And the actual rendering resolution that we need to render is even higher than that, about 1.4 times higher, because the images submitted by the game can't be directly displayed on the HMD. Instead, they need to compensate for the lens distortion, because the lenses cause visual distortions, which results in loss of detail. So that's why we need even higher rendering resolutions. So we have a wide field of view, and we're rendering at a high resolution, and that negatively impacts performance. But to achieve presence, we need to render at a high frame rate. Both Vive and Rift have 90 Hz displays, and games should ideally render at 90 frames per second. This means we have about 11 milliseconds to render, to prepare and display each frame. That's two separate scenes in a very high resolution, since we have to render two eyes. So how do we do that? Well, the most simple approach is to do it in multiple passes. It's slowest and it's easiest to implement. We'd basically prepare and execute rendering commands for one eye, and then we do it all again for the other eye. But this is very taxing on both the CPU and the GPU, and it often requires lowering the visual fidelity to achieve the desired results. Now the question is it possible to have both high performance and higher visual fidelity? Well, in a way, yes. The reason for this is although the rendered scenes are different, because we have stereoscopic vision, they're also very similar. Both scenes for both eyes mostly contain the same objects, with just some that are visible only on one eye. And we'll base our optimizations on this fact. So the first optimization method, which practically halves the CPU workload for graphics processing, is single-pass rendering. It does exactly what it says. Instead of processing all the objects twice, we go through all the visible objects and submit the work, GPU work for both eyes at the same time. This can be done in many ways. Some of those are instancing, geometry shaders, and we can also do it with proprietary vendor extensions, which both NVIDIA and AMD have, which is the course we decided to take. I'll explain why in a minute. So the other optimization is the multi-GPU rendering. Unfortunately, this is not for everyone. Most users don't have 2 GPUs, and we need them for this. So we need to have at least 2 GPUs in SLI or Crossfire. And this decreases the GPU workload by splitting the work between 2 GPUs, so that one renders the left eye and the other renders the right eye. Rendered image from the other GPU needs to be transferred to the primary GPU to be displayed on the head-mounted display by the VR system. There was actually some talk last year about having the VR APIs themselves, like SteamVR, be multi-GPU aware. So you could send the rendered scene on the secondary GPU without actually moving it to the main GPU, so that the distortion effect could be applied on the same GPU. That would lower the impact on the main GPU. And then the system would copy it back after distortion correction for display. But unfortunately, I couldn't find any recent information about that, and I'll be glad if anyone here knows more. In our experience, multi-GPU is the most simple way, actually, of implementing single-pass rendering. So it's a good starting point, and it's done through proprietary extensions. Which both AMD and NVIDIA have. And this gives you control, these extensions, over which GPU will process the following rendering commands, and also they have functions for transferring resources between GPUs. For us, multi-GPU support was the main reason we chose vendor extensions over geometry shaders or instancing for single-pass rendering. So, our first attempt at multi-GPU rendering was to just tack it on onto our existing 2-pass renderer. So we added functions to give the commands for the left eye to one GPU and the commands for the right eye to the other GPU. Unfortunately, what we got was a complete mess. The reason for this is that our engine has many optimizations about state changes. So we don't do a state change if that state is already set. This is usually great, but it caused us huge headaches. Interestingly, we weren't the first one with such problems. Actually, Mikhail Mironov from AMD gave a talk at last year's Oculus Connect about how they had to go around DX11 optimizations, which DX does internally, to even make LiquidVR work. The talk also explains multi-GPU rendering on AMD in great detail, and there will be a link to the video of the talk on the last slide of the presentation. So let me explain with a simple example. So let's say we're rendering just a single textured object. So we'd first set the GPU affinity mask to 1, so the following commands go to the first GPU. We then set the constants for rendering, and then bind the texture. This will bind the texture on that GPU, but not on the other one. We draw the object, and everything will be fine. We then set the affinity to the other GPU. We'd set the constants, we'd bind the texture, but the engine is optimized, and it thinks the texture is already bound, so it doesn't do anything. Texture is still bound on the first GPU, and it doesn't get bound on the other one. We draw the object, transfer the image, and it's a mess because of the missing texture. The texture is just an example. It could be anything else. It could be a vertex buffer. It could be a state change, or any number of things. So we had we had a lot of those issues which we needed to fix. And it's not that those issues are too hard to fix. In this case, it's just a simple change to make the texture remember if it's bound per GPU instead of having a global bound texture. But the point is, it's a lot of work that would ultimately go to waste because we didn't even want a two-pass GPU renderer. It was just a start. We'd want single pass because then we'd get the CPU side benefits as well. And the extra benefit is we don't need per GPU state tracking there because the single pass does everything in one go. So we decided to bite the bullet and move on to single pass rendering. This made those issues non-existent. It made things much simpler. For the same scene, we now set the affinity to the left eye GPU and then set the left eye constants. We then set the affinity to the right eye GPU and set the right eye constants. And after that, we'd set the affinity to both GPUs. We'd bind the texture, which then would get immediately bound in a single command to both GPUs. And then we'd draw the object, which would get bound which would get drawn on both GPUs, each with its own set of constants, and we get two different images with just a single draw call. This way we enjoy both the GPU and CPU side benefits, and we got rid of a lot of nasty multipass bugs to fix in the engine. So this was a lot better than our last approach, but we still had a problem. The problem for us was a large catalog of shaders that all worked with different sets of constants. In our engine, each shader has constants in different locations. So a view matrix in one shader can be in one location, on the other shader in a completely different location. And this would mean we'd have to upload a lot of per GPU data, which requires a lot of affinity mask changes, which severely decreases performance because the vendors, the NVIDIA and AMD, don't recommend setting GPU affinities too often. Of course, this might not be a problem for some of you if you try to go down this road, because view and projection matrices in some engines are in fixed locations, regardless of the shader. And those engines wouldn't have any problems there. The other problem for us was that we also wanted to implement single pass rendering on a single GPU in the future, where we wouldn't be able to have the different values in the same constant buffer, since the memory there is the same. And in multi-GPU, we have two different memories which can contain two different sets of data. Our solution to this problem was to actually upload constants for both eyes to both GPUs. So each GPU has access to both the left eye and right eye data at the same time. But the GPU needs to know which eye scene to draw, so we added a single global constant, which was accessible to all shaders, which is set to 0 on the first GPU and to 1 on the other one. We then use the left eye or right eye data passed to the shader depending on that constant. Let me explain. So we'd first set the affinity to the left eye GPU and set the constant there to 0. On the right eye GPU, we'd set a constant to 1. Then we'd set affinity to both GPUs. And then for each object, we'd set a constants with data matrices for both eyes. And then when we draw the object, the shader chooses either the left eye or right eye data, depending on the VR eye constant. What's interesting to note here is that sending data for both eyes doesn't actually mean that we have to send twice the amount of data to the GPU. Actually, only one matrix, for example, let's say a view or projection matrix, needs to be sent completely. For the other one, we just need to send data that is different. What we've noticed in the case of view and projection matrices, this is only their first row, the x-axis row. Since the only difference between the eyes is their horizontal offsets, that's in the view matrix, and in the projection matrix, that's the direction of the frustums, which is only different on the x-axis. This means that only the x-coordinate in view and clip spaces will be different when transforming a point for each eye. We actually got this idea from NVIDIA's single-pass stereo extension, which actually only takes the different x position value for its right eye position. It doesn't get the entire position. But, of course, there was a problem here as well. When we originally tested this, it was done on Oculus, and we didn't have any problems there. But then we started working and testing more on the Vive, and we saw a problem that we had a small vertical offset, barely noticeable, but kind of there, and it just messes with you a bit. Then we found out what's the reason for this. Actually, Vive has individually calibrated projection frustums for each eye on each device. So no two devices are actually the same. And each have the different, slightly different frustum edges. So this means that the y-coordinate could be different in clip space as well. And that would make our optimizations worthless. And even worse, it would prevent NVIDIA single-pass stereo from working, since that only gets the x position. So here in the given example, we can see that the vertical frustum edges, colored red, are different for each eye. To get around the problem, we actually rendered each eye at the maximum FOV for both eyes. But then the FOV wasn't correct on both eyes. So we needed to compensate for that. So we render at the maximum extent, but we only send a smaller part of the texture that actually matches the vertical FOV of each eye. Steam's SteamVR submit function thankfully allows for that, because you can specify the exact extents of the texture that you're going to submit. And you can easily calculate those extents and ratios from the getProjectionRaw function, which returns these values. So now each eye gets its correct view, and we only have a bit of leftover pixels that we needed to render to get both eyes with the same frustum. Okay, so on to the single GPU, single pass. So when we extended this approach to rendering on a single GPU, it was important to make it work with the same set of shaders and to make it both methods work as similarly as possible to minimize the number of bugs that will only happen when rendering in one way but not for the others, which would be a huge problem for testing because there are a lot of combinations there. So that's four different rendering methods next to the multipass, so that would be 5 times longer testing. So that was not possible for us. So what we did, and what the problem was, that in multi-GPU, images are rendered to the same viewport of on the same render target. So that's in multi-GPU. It's just the content of that render target that is different, so the memory is different. In case of single GPU rendering, we can't do that since there is only one memory. We can't have different images in the same viewport of the same render target. And we also can't specify a different render target for each eye. Instead, what we can do is to use a render target array or a wider render target that contains both views side by side. We decided to use the side-by-side rendering to avoid compiling a different set of shaders, because we need to do that because then we'd have to use texture arrays in shaders instead of regular 2D textures. And it was also a nice exercise for us to see how we might implement multi-resolution rendering in the future. Also, side-by-side render targets are double their usual width, of course. And to make things more simple and to avoid having too many conditions for this in the code, we basically lie to the higher level code about the size of the textures. So if someone asks for a render target that's 256 pixels wide, we'd create it as 512 pixels wide. But when querying for the texture size, we'd say it's 256 pixels wide. The outside code shouldn't even care about how the texture is handled internally. This minimizes the amount of code that needed to be aware of multi-view rendering. Only the shaders and some of the lower-level rendering functions needed to be aware of the actual texture sizes. What's important to note that some of these functions were copying and clearing operations, which really must be aware that they're working with multi-view textures, because when you're clearing a part of the render target on a higher level, which even doesn't know that it's working with a multi-view texture, we need to clear both sides, the left and right side. And also when copying, we need to take into account if the source or target texture is multi-view to account for that. So let's talk just a little bit about the extensions. AMD does single GPU, single pass rendering through its LiquidVR multi-view extension, which is supported on all recent AMD cards. On the other hand, NVIDIA single pass stereo needs special hardware to work. So it's not supported on Maxwell or older GPUs. It's Pascal only, which is both good and bad. It needs it's not supported for all users, unfortunately, but we do get performance boost because of that hardware support. So how do we draw to a render target like that? It's fairly simple. We just let the driver know that we're going to use 2 viewports instead of 1 for multi-view rendering. And the right viewport is always the same size as the left one, just offset to its side of the texture. And in the shader, we have a predefined constant, the second point, which is vendor specific, which we use to determine the currently rendered viewport. And this index basically behaves the same as the VRI constant that we used in multi-GPU shaders. We use it the same way. So using it, we determine which view-dependent constant data to use in the current shader. Reading from such a render target is just a bit more complicated. Since the texture is twice as wide, we need to sample left-hand side when rendering the left eye scene and the right-hand side when rendering the right eye scene. We do this by multiplying and offsetting the UV coordinates of the texture before sampling. It's similar to atlasing. And to choose the correct size, we also use the viewport index. We use the given offset to convert the use the given index to convert the UV coordinates from 0 to 1, that's the usual UV range, to 0 to 0.5 for the left eye and 0.5 to 1, so the right side for the right eye. The most difficult part of implementing this was going through all of the shaders again and applying the offsets at the right place. Those were mostly various post-processing shaders, since they usually sample from render targets. What's also important to note is that not all render targets are multi-view. For example, the shadow buffer. And also some shaders can be used both to sample from regular textures and from multi-view render targets. And in those cases, it's important to apply the offset conditionally in that case. We actually do this by passing an additional Boolean to the shader which specifies whether the texture is multi-view or not. But it's not often needed because the post-processing shaders, for example, always work with multi-view textures. It's just some specific cases. So now that we got all this covered, we have single pass rendering on multi-GPU and also on single GPU AMD systems. But it's still not enough to have it work on a single NVIDIA GPU. Why is that? This is because, like I mentioned earlier, Pascal hardware has special optimizations. It actually executes the vertex shader only once for both rendered scenes. This is good because we get a GPU performance boost along with CPU benefits, as you'll see later in the graphs. But it requires a bit of extra effort. We needed to change basically all the vertex shaders because the single vertex shader pass now needs to calculate data for both eyes because it's done only once. And output sum that's needed to the pixel shader. Position for the right eye is handled by sending it to an output with the NVXWrite semantic, which only takes the X coordinate. So instead of sending the data for only one eye to the pixel shader, we send both, and then choose in the pixel shader which set of data we want to use, since we have the eye index there. Also, to avoid having separate code paths for that as well, we now actually use the same approach, so calculating all data in the vertex shader for AMD and multi-GPU rendering as well, which is a bit suboptimal, but it's a lot simpler to maintain. The only difference in those cases is when rendering the right eye, we actually take that calculated X offset and apply it to the main vertex position output. So we get the right eye position instead of the left eye position in the main output. And this condition is the only eye-dependent part in our vertex shaders. And it's done only when not working on NVIDIA. So this is a bit of a scary slide. But it's basically a high-level pseudocode overview that basically explains how VR rendering works in the Sirius engine. So when we start, we need to check how we're rendering. If we're rendering with multiple GPUs, we first need to set per GPU constants. So we set affinity mass to 0, left eye, right eye, we set 1, that's it. And then we set the affinity to both GPUs. Now we're done with that. For single GPU, we just have to call the API functions that sets up side-by-side rendering. Then we start rendering objects. We set the matrices and other constants for both eyes in the constant buffer. In the vertex shader, we calculate vertex positions and other data for both eyes. And unless doing single GPU NVIDIA, we have to move the right eye position to the main vertex output when rendering the right eye scene. So next is the pixel shader. For the most important thing there is to get the eye index. We have 3 ways of doing that. For multi-view, we get it from the per eye constant buffer. For AMD single GPU, we get the index for using the get viewport index function. And for NVIDIA single GPU, we get the index from the viewport array index pixel shader input. So now we have the eye index, and we use the index to select either the left and right or the right eye sets of constants or shader inputs. And in single GPU mode, we also use the index to calculate the offset for sampling the render targets. So finally, after we're done with rendering all objects, if we're using single GPU, we're done. And if we're doing multi-GPU, we have to transfer the image generated, rendered on the secondary GPU back to the main GPU. Yeah, so basically that's the high-level overview. That's what our engine basically does. So now we'll take a look at some graphs to show the performance difference between the various rendering modes. So in this image, on the red color on gray, not such a good idea. I hope you can see. So on the left, you can see the 2-pass renderer, which is the dumbest way of rendering anything in VR, running on NVIDIA GTX 1080. In the middle, you can see our optimized 2-pass renderer, which we had to do for Maxwell since it doesn't do single pass. What it does differently is that it actually processes shadows only once, which makes sense. And it also does some object pre-processing only once for both eyes. So it's optimized. And on the right, we have the single pass renderer. As you can see on the top graph, the CPU usage for the single pass is considerably lower, even when compared to our optimized renderer. And compared to just the dumbest way of doing things, it's almost twice as fast. The lower graph shows GPU usage. By the way, this is all taken from the performance graphs in SteamVR. I just stitched a couple of results together. Yeah, the lower graph shows GPU usage. It's lower in the middle because we do shadows only once, so that's that. And it's also a bit lower on the right because this was done on NVIDIA, and as I said, we process vertices there only once for both eyes. On AMD, the top graph would look roughly the same as it does here, and the bottom graph would probably show no significant difference between the middle and the right sides because the GPU work is basically the same. This is the multi-GPU comparison. Here we can see the comparison between the optimized two-pass renderer running on a single GPU. And on the right, you can see single-pass multi-GPU with two 1080s. The scene chosen here wasn't very demanding on the GPU, sorry, on the CPU. As you can see, it's just a couple of milliseconds, but it was very demanding on the GPU. It's very high resolution with anti-aliasing. And as you can see on the left, a single 1080 can't handle this scene at stable 90 frames per second. While on the right, you can see that running with multi-GPU single pass, the two 1080s have no problem running the scene at stable 90 frames per second with also some space left to do more things. So basically, all of this, as you can see, was a lot of work, especially going through shaders 3 times. First, to set up the per eye data for multi-GPU, then multi-view sampling for single GPU, and finally single vertex shader for both eyes for NVIDIA single GPU. But to make VR games, it's really worth it because VR is a lot less forgiving on bad performance than desktop games because bad frame rates can literally make people feel sick and not want to play VR anymore. What's interesting is that what we did could be and probably will be extended with multi-resolution support in the future. And it's also interesting that it could have its uses in a non-VR rendering. So basically, we could render cascaded shadow maps in one go using this approach. Unfortunately, we didn't have the time to try this until before. Hopefully, we will in the future. So thank you for your time.
Right. Thank you for the presentation. I have one basic question. This is all about D3D11. Have you considered or tried D3D12?
Test. Oh, it works. Okay. We didn't try DX12. And yes, this is all based on DX11. I should have mentioned that. But we did try Vulcan. And we're working with that. And we'll probably have single pass rendering there. We'll see how. We're still working and we're in early experiments with that. We'll probably try something like playing the command buffer twice with just different sets of constants, something like that. And if vendor extensions become available for those APIs, we'd also use them as well because we have then the more potential of them being more performing. I believe the NVIDIA extensions I talked about today is actually also available for DX12 as well. Because to get the hardware support that's implemented in Pascal, you need to use their extension. You can't get that just from plain old DirectX, be it 11 or 12.
So how did you manage an unextended Vulcan that can't communicate between two GPUs without using a CPU?
Between two GPUs?
Yes. Unextended Vulcan. Because
no, that's not possible, I believe, because you need to have some extension that would allow you to use two GPUs. And that's
mean, you can use two GPUs, but you can't communicate between them without CPU.
Yeah, and that's a problem. There are some suggestions, I believe, in Kronos, some like early things with extension plans that allow just that. But I don't know for now more about that. So they are working.
Okay, so the bottom line is that there are some existing extensions for D3D12 by NVIDIA, as you just mentioned, right? Yeah. So if I Google a bit, I'll be able to find.
Yeah, you just search for VRWorks which is their extension, and you'll find that it's available for DX12 as well. Since our engine doesn't support DX12 at the time, I can't really say much more about that since I didn't experiment with that.
All right, thank you.
Someone else? Okay, so one more time. Thank you very much, Karlo.